Systems of linear equations, graphing, substitution, and elimination methods. For systems of linear equations, our goal is to be looking for an intersection point between two different linear equations. Now, that intersection point is called the solution. There are three different methods of doing this. We could do the graphing method, substitution method, and elimination method. And regardless of which method you choose, you should be getting the exact same answer. So when in doubt, you could always try more than one method just to check your work. Now, graphing with a calculator or computer tool would be ideal because it's going to help you identify that exact location of the solution. If you're just sketching it on paper with a graph, sometimes it's hard to see if your answer should be a fraction or a decimal result. So substitution and elimination method are the algebraic methods of solving that we typically focus on the most to find those solutions, especially if we're not going to get whole number answers. So here's our first method, graphing. The steps in order to do this is we're going to graph both of our lines individually. And I recommend putting both of your equations into y equals format. So that's your slope-intercept form. Then graph from there. You can use a t-chart, you can use x and y intercepts, or you could use that slope and y-intercept. Once you have them both graphed, look for where they intersect. So here's our first example. We have y equals 2x minus 3. So using our slope and y-intercept, negative 3 is our y-intercept. So on our y-axis, we'll go down 3 and make our initial point. Our slope is 2. So for slope, we always want to write it as a fraction. So in this case, that means we are going to rise 2 and then run to the right 1. So from your y-intercept, go up 2, right 1 to get your second point. Now, the nice thing about slope is you can repeat that process. So from your new point, you can go up 2, right 1, and keep on going. So this is our first line. So go ahead and connect those dots. Put little arrow points on the end. And now let's graph our second point. Now, x plus y equals 0 is not in the form of slope-intercept. So we're going to get there first. So to get y by itself, we'll subtract x from both sides. And then we're there. Y equals negative x is our slope-intercept form. Now, if you want to put that plus 0 in the back, it might help you see it a little bit better. But that's your y-intercept in the back. So for our second equation, we have 0, 0 is our y-intercept. And then our slope is a negative 1. So negative 1 over 1, that's our rise over run. Because it's negative for rise, we're actually going to go down 1, then right 1, and put a point. Down 1, then right 1, and put a point. Once you get a couple points on your graph, you can connect them up. And what we're looking for is their intersection point, their solution. So we can clearly see on this one, we have it marked that this is where they intersect. And that is the ordered pair 1, comma, negative 1. 1, comma, negative 1. We'll want to write our final answers as ordered pairs. So now let's try substitution method. For substitution method, your steps are going to be to solve one equation for one variable, plug that result into the other equation, solve for the remaining variable, because there should only be one at that point, plug that answer back into your first equation to get the last answer you need, and then assemble your results as an ordered pair. So for our example, we have 4x minus 2y equals 6, and y equals x plus 1. So what we mean for that first step of solve one equation for one variable is we're looking for an equation like this. Notice the second equation already is y by itself. That's perfect. That's what we ideally want to have. So sometimes when it's already set up this way, substitution is then ready to go. If it wasn't like this, you would just shuffle around the pieces to either get x or y by itself. So for step 2, we want to plug the x plus 1 into the other equation for y. So we're going to plug it in there. So if I pull it off to the side, we've got that top equation, 4x minus 2, and instead of y, we're going to plug in x plus 1 equals 6. So this is that step 2 right there. We just plugged it in. And now what we're doing is we're solving for the variable. And if you read through that equation again, the only variable in there is x. So that's the one we're looking for. So in this case, we're solving for x. So we can distribute. We can combine like terms. We can add the 2 to the other side. And our last step is always the divide. So we keep going all the way down until we've solved for that variable. So all of these steps in here are step 3 to get to x equals 4. Now we're going to take that x equals 4 and we can plug it really back into either one of our original equations. It's either the 4x minus 2y equals 6 or the y equals x plus 1. And actually, I'm going to plug it into that second one, y equals x plus 1. That one's going to be probably a little easier to plug into. So when we plug it in, we get y equals 5. That was step 4 right there. We plugged it back in, and I'm going to even put here either equation. It really doesn't matter which one you use. And then the final step is putting together your final answer. So keep in mind your ordered pairs should always be x, then y. So we found 4 for x and 5 for y. That would be your intersecting point, or like we like to call it, the solution. Now let's look at elimination method. So our steps here are to check that both equations are aligned. That means they are going to be stacked up. X is on top of each other, y is on top of each other, equal signs, and your constants. Then you're going to multiply your equations to create additive inverses for either variable. You're then going to add your rows together, solve for your remaining variable. Since you just eliminated one, there's only one left. And then you're going to plug that result back into either equation and assemble the results as an ordered pair. So step 1, check that both equations are aligned. That would be like it's already set up down here. Notice your x's are on top of each other here. Your y's are lined up, your equal signs are lined up, and then your constants are lined up. That's what it means to be aligned. You don't want one to be solved for y, and one to be in standard form, and one to be something else. You want them to be similar in format. So then we're going to be looking at each one of these, and we're going to try to create additive inverses. What that is it's the same number in front of the variable with opposite signs. So additive inverses would always add up to 0. So if you're looking at our x's in the front, we have 2x and 3x. We want them to be the exact same number, just opposite signs. So the easiest way to do this when you have different numbers on them is to crisscross. So if the second row starts with a 3, we're going to multiply the whole top row by 3. And if the top row starts with 2, we're going to multiply the whole second row by 2. So 3 times 2, you get 6. 2 times 3, you get 6. So this is going to give you those same exact numbers for both. The only other thing we need is we need them to be opposite signs. So we're going to multiply our whole second row by a -2. So what we're looking to have is our top row is going to be 6x, and our bottom row is going to be -6x. So let's try this. So we're going to multiply by the whole row. So 3 times that whole top row becomes 6x minus 3y equals 12. -2 times the whole second row. -6x plus 6y equals -18. So we just did that second step right there. The third step is we're going to add these two rows together. This is why we wanted everything nice and lined up. So 6x minus 6x cancels. This is where it gets the name elimination method. We've eliminated a variable. -3y plus 6y gives us 3y. 12 minus 18 gives us -6. That was our step 3. Now step 4, we're just solving for that remaining variable. The only one left is y. So we'll divide both sides by 3. And we get y is -2. We can plug it back into either one of the original equations. Doesn't matter which one, so I'm just going to use the top one. 2x minus, and we'll plug in y equals 4. And we're just reducing. Until we get that other answer, x equals 1. So our last step, putting it together for that final answer, it's always x, comma, y. And again, that is your solution or that intersecting point if you were looking at the graph. So we've covered graphing, substitution, and elimination. And there's one other thing to mention here. And that's the tricky. Sometimes when you're solving these problems, things aren't going to go exactly as you planned, and you're going to panic for just a minute that it didn't work. So if you're ever solving and you notice that your variables just disappear completely, you might panic, check your work, make sure that it happened on purpose. And if that happens, you've got 2 special cases to look for. So if you think back to how you could graph 2 lines on a coordinate plane, you could graph 2 lines and they intersect. That's like all of the problems that we've just seen here. We had 3 of them where they crossed at one intersection point. But there's technically 2 other situations that could happen. If you had parallel lines, so you had 2 lines that happen to run side by side, they're equidistant apart the whole time, they never cross. So in fact, we call that no solution. There's no intersecting point between them. You'll also see it termed inconsistent. And so when you're solving, your variables happen to disappear. And what's most important is what's left. If your variables cancel and you're left with a number that doesn't equal the number on the other side of the equation, that's your parallel line situation. So you might be solving and you're going through the process and all of a sudden you get 2 equals 0. If you ever get to a point where the 2 numbers that are left don't equal, there's no variables, that's your parallel lines. Now, the other situation that could happen is that maybe your 2 equations are identical. So if you go to graph them, they end up being the exact same line on top of each other. So I always draw it with double arrow points on the end just to remind myself that's one line on top of the other one. So in that case, when you're thinking about where they intersect or where they're touching each other the whole way through that line. There's many spots on there. So that's why it's the infinitely many solutions. There's lots of correct answers to this. So in those situations, when you're solving, the variables disappear, the 2 numbers that are left are equal. So you might be solving and all of a sudden you get down to 3 equals 3. The numbers on the 2 sides do equal, then you've got the infinitely many. If they don't equal, that's your inconsistent or no solutions. So keep your eyes out for those. Those will come up in all 3 of your methods, whether it's substitution, graphing, or elimination. Keep that one in mind.